Okay, Algebra 2. All right, we'll give this a go again. Today we're going to talk about complex numbers. So for complex numbers, first things, we've talked about that already. We've introduced them, we have them there, but maybe I didn't explain, why are we still doing this? Because imaginary numbers seem like they're imaginary. Well, why were we doing that? Somebody came along and said, just as a reminder, they said that the square root of, let's say, negative 24, they thought of that as the square root of 24 times the square root of negative 1. And to make it easier, the square root of negative 1 we just thought of as an I. And so the square root of 24 times I. Now this gets broken down into 6 times 4, and that's 2 times 3 times 2 times 2. And so I get 2 times the square root of 6i. So there's the simplified version of that. But these are imaginary numbers now, and we started going with that. Basically, the mathematicians said, hey, well, what happens if this square root of negative really could happen? And we realized that in our day-to-day life, they didn't think it was happening, but somebody said, well, what if? They played the what-if game, and they developed a whole bunch of math that had i's in it, had the imaginary numbers. And they said, well, if we put those together with the real numbers, we'll call them a complex number, and what can we do with that? So the math people, they went with it, and they did all this different math, and they said they based it basically on the predication of the one idea that the I was the square root of negative 1, and where would that go? Where would we get? They did all this math, and it was great. Except for you guys are studying it now, and you're going, well, if it's so great, why is it there? It's imaginary numbers. Well, we wouldn't still use it unless somewhere out there, we wouldn't still teach it to you unless somewhere out there used it. And there are some applications. Your books likes to talk about fractals, that's one thing. And the other thing that's probably more important is that you're using it right now, or somebody used it to construct the room that you're in. Because complex numbers, it turns out, complex numbers with the real and imaginary part, do a great job of modeling the flow of electricity, in your electrical lines. So electricians or electrical engineers that are designing the building, they know that they can model the flow of electrons and through their circuits, and for your lights and for everything that uses electricity using imaginary numbers. And so that's one of the big uses for imaginary numbers, probably one of the reasons why we still teach it in all of our curriculums. So here we go today on how else do we use this. The first thing we're going to do is we're going to talk about graphing these. It's a very standardized question, a very common standardized question. I found out some of my students were getting it wrong on some of their placement tests and on, they say, the ACT. They're coming back to me and saying, I got some wrong, or they asked me how to do this and I had no idea. And it was a really easy fix. As soon as somebody came back, we said, yeah, we can fix this. Because to graph C at negative 3i, all we have to do, or D is a little bit easier, at negative 3 plus 4i, all we have to do is say, well, when we graph things, we have an x and a y-axis. Let the x-axis be the real part, and let the y-axis be the imaginary part. In other words, the part before the I. And so at C negative 3i, 1, 2, 3, 4, 5, there's negative 5. Let's see if we can do this right. 1, 2, 3, 4, 5, there's positive 5, 1, 2, 3, 1, 2, 3. I don't know if I need more than that. And so C, it turns out negative 3i, wait a second. I can't go with an x value of negative 3 because C becomes the point. What's the real part? 0. What's the imaginary part? 3. It's 0, negative 3. There is C. Where does D end up at? Negative 3 plus 4i. Well, that's the point negative 3, comma 4. So I'd go left 3 and I'd go up 4. Yeah, I do need another one. Left 3 and up 4, and there is my point D. And then, of course, we have point E here at 5, 2, over 5, up 2. There's my point E. So graphing these complex numbers is not that difficult if you just convert it into the coordinate points with the real part first and the imaginary part second. And notice there's no I in there. So that's how we graph it. The next thing they started saying is, which of these numbers is bigger? And so when we think about which number is bigger, really on the absolute value scale, we say, is 5 bigger than negative 8? And we say, yes, 5 is bigger than negative 8. However, is 5 further from 0 than negative 8? And that's an absolute value idea. And the answer is no, negative 8 is a lot further away. It's 8 units away, whereas positive 5 is only 5 away. And so we had this idea of let's compare it to where we're starting at, and let's get one number that tells me how big these numbers are. And it was really easy. They said, well, C, this would make sense. How far is it from 0, 0? You know, how far is C from 0, 0? And the answer is, well, it's right down there, it's 3. So the absolute value of C, absolute value of C would be 3. And that's not a difficult one. The absolute value of D is like how far away is D from the origin? Well, that's the length of that segment. So how long is that segment? Oh, you may see it right here. What do we have going on? We have to figure out the length of the segment. Well, this over here was 4. That was 3. This was 4, right? That was 3 and 4. How do I figure out the length of that? That's right, it's Pythagorean theorem. The square root of 3 squared plus 4 squared. Okay? This leg is 3, that leg is 4. We square them both, we add them together. We get 9 plus 16, their square root. That's the square root of 25. So the absolute value of D is 5. Now don't get confused here. Don't try to put an I in there, because if you try to put an I in with that 4I, that would be 16I squared. It would be minus 16, and we don't want to do that. We take the i's away and just look at Pythagorean theorem. Just square the first part, square the second part. And the third one then, so what is the absolute value of E? Again, that's just Pythagorean theorem. That's 5. We go over here. How far away is that? How long is that segment? Well, that's 5 squared plus, what did we say this other value was? 2? So 2 squared, and then it's square root. 25 plus 4. That's the square root of 29. So we'd say that E is further away from the origin than D. Okay, so the absolute value of E is bigger than that. And that's what we talk about absolute values and, you know, how far away they are. Okay? From there, what we want to do now is let's get into some operations with complex numbers, because now we can graph them. Now we can figure out their absolute value or tell you how far they are from the origin. And now let's go ahead and start putting them together. So we're just going to use A as negative 2 plus 3i, and B is the complex number 4 minus 5i. And we'll go over here, and let's add those. Okay? And let's see what comes of adding those two complex numbers. So we have negative 2 plus 3i, and we have, let's see if I get the right colors here, 4 minus 5i. I don't need the green anymore. These will go good. Okay, and we want to add those two things together. So when we add those two things, it only makes sense that things that look the same get added together. Negative 2 plus 4 and the 3i plus the negative 5i. Notice I changed everything to addition and call them negative or positive. This gives me a 2, and that gives me plus a negative 2i. So in the standard form of a complex number, it says a plus bi. We write this as 2, either plus a negative 2i, and you can get by with the slang of 2 minus 2i if you want. But there we've added those two numbers together. Okay? It's that easy. Add the real parts, add the imaginary parts. Okay? Remember, they're only equal. Well, I shouldn't say that. We're going to get there later. I misspeak. Let me go back. So what happens if I switch this to a subtraction? So we have that minus that. Well, here's the key. Remember, you're subtracting this whole other number here. Okay? This started off as a plus b, and now this one is a minus b. We've got to subtract the whole thing. So this is still negative 2 plus 3i, but then this will be negative 4, and subtracting a negative is adding a positive, really a positive 5i. And now when I put the common things together, we get negative 2 plus negative 4, and we get plus 3i plus 5i, and this combines to be negative 6 plus 8i in the standard form. Okay? So subtraction is nothing more than adding the opposite. Make sure that you distribute that negative sign to both of those things in there. Okay? And so, pretty good. See how much time I have left. Okay, about 4 minutes. And now let's see if we can build on the pattern of i's. And I think I did this once before, so I'm going to try to do this fairly quickly. Remember that I equals the square root of negative 1. I squared, by definition, then is negative 1. I cubed equaled I squared times I. Well, that's negative 1 times the square root of negative 1, otherwise known as the opposite of I. So I'm just going to boil that down to the opposite of I. And I to the fourth, remember, is I squared times I squared. It only makes sense we should break that up. Well, that's negative 1 times negative 1, so that equals 1. So I to the fourth, that's an important one, is negative 1. Excuse me, negative 1, is positive 1. Now, here's the key. When I get to be I cubed, I to the fifth, I can think of it as I to the fourth times I to the first. But I to the fourth was just 1, so that's 1 times I. I to the sixth would be I to the fourth times I squared. So that's just going to repeat. That's going to be negative 1. I to the seventh is going to be I to the fourth times I cubed. Remember, this I to the fourth right here is just 1, so that's the same as I cubed. And I to the eighth is I to the fourth times I to the fourth is 1 times 1 is 1. Likewise, I to the ninth is I to the fourth times I to the fourth times I. So this repeats. I to the 10th is I cubed. Excuse me, negative 1. What am I thinking? 10. I'm in too much of a hurry. I to the 10th is I squared. I to the 11th is I cubed. And then I to the 12th is the same as I to the 4th, which is 1. There's a pattern. So I to the 43rd isn't as much as what is I to the 43rd. It's saying how many times does 4 go in here and what's left over. You know, that's I to the 4th, I to the 4th, I to the 4th, a whole bunch of times. And then it's I to what power? So that's 43 divided by 4. It goes in there 10 times. I don't really care about the fact it goes in 10 times. 10 times 4 is 40. And 43 minus 40 is 3. So it goes in there 10 times. So I'm going to have I to the fourth 10 times. Well, that's each time it's just 1. And then we're going to have 3/4, that remainder of 3. So that's going to be 3. So I to the 43rd is the same thing as I cubed, which is the opposite of I. So, what happens if I take I to a large, like 249? I'll just take 4, bring it into 249, 6 times, 24, 0, 9. 4 goes into 9 twice, 8, 1. The remainder is 1. What does that mean? It means I to the 249th acts the same as I to the first, because the remainder was 1. So I have I to the fourth a whole bunch of times, but then I have I to the first 1 time, and I to the first is just I. Okay? So hopefully I kind of taught that a little bit earlier and forgot that it was coming up again. And so you had a preview of it, and now you've had a second time through. Hopefully that makes sense for the repetitions. Now, this video is going to lead into another video that I did earlier, but since I had some technical difficulties, I had to delete the other one. So the next video, you should be able to take A times B and go from there, these same A and B's, but you're going to notice that things are going to change a little bit, because I did that one previously, but for some reason YouTube wouldn't take it. So if all goes well, you'll get a new video to finish this off, and hopefully that gives you the ideas of complex numbers.